hear them now.
Oh yeah, like it's
now we can hear them.
So like,
Can you hear me?
You guys hear us? You can get that.
I'm
Yeah, we can hear you.
Oh, perfect. Nice one.
Then I can't have my feet up. Oh, okay, you're fine then.
Rent a car and sleep.
Can you guys hear Levi?
That was actually my original plan.
Yeah.
Just stay for 2 days.
Okay. Do you like the setup like this?
It's excellent.
If you
Okay,
could find a
perfect.
safe
Thank you,
place to
gentlemen.
park, that wouldn't actually be bad
Okay.
for you.
Yeah,
safe
find a
place.
Dunkin' Donuts. I can guess that we are waiting. One more person.
oh yeah.
You have your microphone?
Oh my god.
Hey Daniel,
Yeah.
I haven't heard anything from you.
What do you mean?
We supposed to meet yesterday, right?
Oh,
I emailed you yesterday. You didn't even reply my email.
Yeah, fancy, right? I turned
Oh.
it sideways.
I guess I
Ooh.
haven't seen it. I
You
was
didn't
busy.
see it?
I didn't see it.
You didn't check the email for 2 days?
I do. I check it like once a week.
Once a
week. Yeah, I'm really bad with that stuff.
Where did I put my cursor?
So tomorrow? Yeah. No excuses tomorrow. Yeah, I was just busy last week.
She'll be out of Fargo next week.
Huh?
She'll be out of Fargo next week.
She'll be out of work.
Soon.
Landlord business.
So,
Yeah, that's true.
Oh, this is a bummer.
That's why I check in the morning and whenever it beeps
Oh.
that.
I think it's fine to start.
Okay. I was gonna bring the paper with me because I wrote notes on it, but I left it at my
Can you get a couple?
place. Oh yeah. Which one is the one that I use? Is it this one?
Yes.
Okay. Alright, so I finally decided to go back and try and actually figure out why I was doing my research in the first place. So I just did some research on cadmium sulfide quantum dots that are capped with Thiol ligands. The paper that I'm reviewing, which is this paper, is a review paper. So I'm reviewing a review paper, and yes, I know it is 8 years old. Don't judge me. But this is the paper that relates most to what I'm doing research on, and also it references our collaborators multiple times in the paper. So that was pretty neat. So I was like, you know what, I'm just gonna go with it. So, anyways, that is the paper that I'm looking at right now. Okay, so the first thing that I needed to figure out, which I didn't know until this week, was that there was different types of core shell quantum dots. So the cadmium sulfide quantum dot is a type 1 quantum dot where the outside, so the valence band and the conduction band of the shell is higher and lower than the valence band and conduction band of the cadmium sulfide core, which means that the core doesn't really influence too much about the chemistry of the doesn't influence the chemistry of the surface that much. So it can basically be considered a cadmium sulfide quantum dot because it's basically the same thing, which is why when I did my research on it, I didn't put a cadmium sulfide core in there because there wasn't really a need for it because it had the same chemical properties as just a regular cadmium sulfide quantum dot. Yeah, so these are the different types, which I didn't know about until very recently. So, anyways, this is what we're looking at here. And then there are different types of synthesis. I cannot go into much detail about it. I looked into it for 4 hours and I still don't understand anything, but I know a little bit. So there's a co-injection method where you use the Thiol ligands as a precursor, which gives a cadmium sulfide quantum dot the sulfur of it. So basically it dissociates the top of the thiol, which I'll show a picture of in case you don't know what thiol looks like. and the sulfur is donated to the quantum dot. So you put a certain amount of cadmium in there, and then the sulfur comes from the thiol, which makes it a very stoichiometric structure. So there's no like cadmium enrichment or anything like that, because it's very like 1-to-1 ratio. Otherwise, the sulfur won't deprotonate. Not deprotonate, but it won't dissociate from the molecule. And then it also allows for excess thiol to be present on the surface from the get-go. Otherwise, you have to do some sort of exchange, which I cannot tell you much about at all, but I read about it. So, anyways, if you have excess thiol in the solution before it starts, and you make a quantum dot from using the sulfur from the thiol, and you have leftover like thiol, then it just happens to be on the surface of the quantum dot once the ratio is met between the cadmium and the sulfur. And then there's this one, which is, I think it's pronounced SILAR for the acronym. But basically it's just adding different layers at a time, so like one layer at a time of the cadmium and sulfur, so then you just stack them, which is, they're both relatively simple to do, well simple, but they're both relatively the same to do, produce kind of the same results, but we're looking more into like this kind of method rather than this method, because no thiol is present, and all of the, like, it's like passivated completely by the oleic acid and amines. So in order to put any thiol on the surface, you'd have to switch stuff, and I don't know how that works, so please don't ask me about that. But yeah, so there's no thiol present initially. And then amine is known to deprotonate oleic acid, so then the surface has a negative charge from the oleic acid and needs to be balanced out with enriched cadmium, which I feel like is not that great for like a simple system that we were kind of looking at before. So if you're going to do this kind, it's probably going to have some cadmium, some extra cadmium on the surface due to the oleic acid being there. So. Okay, and in the paper, I specifically focused on thiols, but there's different ligands that are present. I wasn't expecting you guys to be so quiet. Anyway, sorry. There's different ligands that they talked about. They talked about topo, which I'm not even going to attempt to pronounce that, which is insoluble in a polar solvent, which is like if you want any sort of biological applications, that doesn't work out well. So that's why we're kind of looking at thiol, because thiol is soluble. And then
you cannot pronounce, but can you provide the chemical structure for topo?
Oh no, not off the top of my head. I could definitely look it up, but I don't have it here. I actually did have it here, but I left my paper.
Can you reconstruct it based on the naming?
No.
Phosphine oxide?
I mean, no, I haven't gotten to that point in
Do
chemistry.
you remember the structure of DNA?
Roughly, yeah. I mean,
So it has bases, it has sugar, right?
yeah,
And it has the phosphate groups.
okay.
So you remember how this phosphate group looks like? No?
I think I do, but like it's been a while since I looked at it, so I couldn't do it off the top.
I know
of
who
my
can
head.
help you, right?
Yeah, so it has a central phos.
Can you maybe use a drawing
I can
touchpad
do
or
that.
Here we have a little whiteboard if you want.
or in a board, yeah, so then you can just show to everyone.
Okay. So we're doing the topa or the phos?
Well, let's do topa, and then I guess then this will be clear where the phosphate goes.
So for topa, it would have a central phosphate group, and then we would have double bond with oxygen, correct? And then I got a thumbs up in the back. So and then we would have.
And this Thiol stays for tree, I guess. How it's in the Greek or Latin? Trial. And O stays for the, I think, octa or something like this, which also comes from the Greek 8.
So
Yes.
How to pronounce
we
it?
have 3
Same as
three octal groups
Oct-
on here.
Actyls, how we pronounce it?
So,
Yeah, C8, H17,
well,
right?
I wrote it as CH2 times 7.
But there are
CH3.
8 carbons in the chain.
So yes.
Yeah, I would not have gotten there.
And in DNA, they don't have, of course, this carbon-based groups. It's just oxygens, right? So
I mean, yeah, I've seen it a million times, but I've never like had to pay
Oh, pay attention
to
next
it.
time.
So, okay.
And it's attached to the quantum dot through the oxygen, right?
I did not look into it very much. I've just seen.
It's attached to the oxygen, and these chains are mainly needed for the solubility properties to increase the solubility in a in which solvent this will be this molecule will be dissolved.
Non-polar.
Yeah, mainly kind of not very polar organic solvents would work.
Okay. Sweet.
We're done, right? Thank you.
Yeah, I was gonna put a picture and then I didn't. Now I'm really regretting it. Anyways, it decomposes at high temperatures, which is also not great for any sort of biological applications. And then it also is toxic. I could not tell you why, but in all of the reports, that's what it said.
Are they toxic? Are they really toxic?
They're like not supposed. When I was reading the article, it was like, do not put in sort of any biological applications because they are harmful. So
It's probably not eatable for sure, but I would not call these groups toxic.
okay.
Well, again, comparing to selenium
Yeah.
structures, nothing is as toxic as the quantum dot, but okay.
And then it talked a little bit about a mean, which like had some benefits to it. It creates a stable quantum dot, and it also increases emission, not significantly, but it does in some way. And then also carboxylic acid, which is what I'm going to be working on in the future. It has the same kind of properties to it, but neither of these have the same benefits as thiol as far as the increase in emission. Yeah. Alright. And then this is, I just wanted to show, okay, well you can't really see it, it's in the corner over there. That's what I use to represent the thiol groups, but there's a bunch of different types of thiols that you can use. They talk about a few different kinds in the paper, which I am not 100% familiar with, but I will talk about using a different one at the end. But I just use this because, or like the methyl thiol, is that how you say it? Methyl thiol? I know it's meth something. Anyways,
Can I ask a quick question?
Yeah.
Do you have a picture of all of these components together at some point or not?
Oh, I didn't put that on there. I do definitely have one. I just don't have it on here.
Okay, so you have your quantum dot, right? And your quantum dot and the shell both are cadmium selenium. True? Is that true?
No. So the core would be cadmium selenium, and then the shell would be cadmium sulfur. But I just use cadmium sulfur.
Okay, so cadmium sulfur for the shell, and then you have the thiol and the amine both connected to the outside of that.
Yeah.
And then the topo dissolving all of this, right?
Oh, okay. Well,
Iso.
I haven't worked with topo at all.
Usually you're not using all ligands. You use isotopa or isoamines, right? Or carboxylic groups.
Mm-hmm.
Well, sometimes it's a mixture, but typically people try to kind of simplify the ligands and not working in a mixture very much.
Yeah.
Okay, gotcha. So in this case, you're going to be using thiol and amine. You won't be using topo.
Okay, well that's what I did for my research, but this is for the paper that is like a review paper. So like that's what I did for my research, but not what's listed here. So this is basically, it's a review paper, so it's a review of a whole bunch of different experiments. So I'm just kind of doing a general knowledge type thing for my benefit and for other people's. So that was kind of my plan of action. Anyway, so I use the thiol with a methyl group on top rather than a huge long chain because it's unnecessary and doesn't react with the quantum dot itself that I know of specifically, except for one instance which I'll talk about later. Okay, so why would we use thiol? A positive of thiol is that the ligands help reduce trap states, which are on the surface of the quantum dot. So it just donates, I'm fairly certain, I don't know exactly the chemistry behind it, but it donates protons to those trap states so that electrons, not protons, oh my gosh, it donates electrons to the trap states, so it's less likely that an electron will fall into that trap state, so it would reduce blinking and increase emission. And then small concentrations of thiol can significantly increase the photoluminescence, which is somewhat equivalent to my first statement. And then the negatives are the low concentrations of thiol, which would produce the best photoluminescence as far as the long stability, like long-term results, like on a matter of days rather than hours. It takes a long time to kind of like see the effects of the thiol, and with large concentrations, it obviously is like a fast decay, so it's not really stable in the larger concentration side of it. And I have a graph of that later. And then also in different pHs, it can deprotonate into thiolate, which I'll talk about on the next slide. Okay, so thiol loses its proton to create thiolate. I know that most of you guys know that, but in this case, thiolate is both responsible for the increase and the decrease of photoluminescence, which is why we're kind of looking at it, trying to figure out whether or not thiolate can, we can like stabilize it, create a mixture between thiol and thiolate to result in like an overall bright quantum dot. So like a couple of studies, I would say many, have shown that thiol is not responsible for the photoluminescent change, it's rather thiolate. And so it reduces the trap states, but at high concentrations, thiolate creates its own trap states. So it's like a give and take, so you don't want, if you have too much thiol on the surface, you're gonna have too much thiolate, but if you don't have enough thiol, then you're not gonna have enough thiolate. And when you have thiol on the surface and you don't allow it to deprotonate at all, nothing changes about the quantum dot. And so there's no necessarily like perks to it. So yeah. Okay, and this is the graph. I really like this graph. It's a pretty old graph. It's from 2005, but I still think that it has relevance. So this is from our experimentalist. So the BME is this, and I don't know the chemical structure of that, but that's what it stands for. And it's just basically the concentration of thiol over like how much it is and over hours. So you can see that without it, the quantum dot, like without any sort of thiol on the surface, the quantum dot is pretty stable and like has a decent quantum yield over 100 hours. And then with like a small amount, you can see it goes up, it like increases significantly. And I can't really tell the difference between these two colors, so I don't know which one is which. I'm assuming that this one is this one.
So your black one having 0 milliliters for your BME ligand, right? So first of all, we don't know what is BME. Second, then it's not a bare dot, it should have other ligands. And what are the other ligands in this case? You said that this data taken, like, again, this is a problem with the review paper. If you go with presenting review paper, you have to go through the citations, especially if you go into the results, especially if you show in the really data, right? You need to understand and you need to explain and be able to really represent the science. Right now, you're just saying, well, some molecule in some concentrations, too much general kind of ideas without really support. So what exactly is the synthesis for this case? In addition that they change the concentration, in which solution, what other ligands are present?
I know this, but I don't want to give wrong information because I.
Do you have your paper with you somewhere?
It
should be in a paper, right?
Yeah, I had all of it and I left it.
In your office?
Yes. I know. I like got here and I was like, yeah. Anyways, it
Is it cadmium selenide zinc sulfide particle?
What?
Cadmium selenide zinc sulfide.
Zinc sulfide? What?
Zinc.
Zinc sulfide. Well, no, the structure of the quantum dot. But if they're not using the ligands, they still should have ligands on the surface. Then Then what
No,
are the
caprate
ligands?
polymer, yeah.
Huh?
They're saying polymer, but
So they do it not in a solution, they do it in a polymer matrix?
a solution, but particle caprate polymer.
No name for the polymer?
Nope, we need to go to the reference.
Well, so again, there might be many, in all the statements which you were making, actually not you, I guess, your statements which you took from this paper, right? So each of the statements really should be supported. You cannot just state without really any evidences. And this is the only evidence so far you're showing at least some data measured, showing the really dependence on the concentration. But again, to understand this behavior and to understand why and really to trust this data, more information is needed.
Yeah.
So we need at least to know the procedures, the synthetic procedures, the kind of structure.
Like I don't understand it, so it's very hard for me to
You don't
relate information.
gain just information from the paper, nothing else. They clearly say in which solution, in which conditions they were doing it, right?
Yeah.
And what exactly is the structure of the quantum dot. So it's cat selenide, zinc sulfide, first of all. First, like your surface here, not cat sulfide, but zinc sulfide.
Mhm.
Right? So it's a different actually structure comparing to what we discussed before. And also, again, so you were claiming that it gives you benefits, right? That your Thiol gives you benefits. But again, looks like if you look on those with zero concentration, which I assume there's like polymer or whatever they use on instead of Thiol, it's not very high quantum yield, but it's very, very stable, right?
Yeah.
And not really changing. In the case of any of these concentrations, right? Some concentration leads to much low quantum yield, but even at higher quantum yields, right? They're going down
Yeah.
for all cases except the green one. And again, green one is also having a lot of changes with time.
Yeah.
Maybe just fluctuations. So I wouldn't really put it very strongly as your statement that it has really benefits for making them very bright quantum dots. Or at least you didn't show, like, this kind of contradicts to your statement there. Because having a quantum dot bright for a couple of hours, and then it's really kind of going almost to, how many? From 50 to 20, almost 3 times smaller quantum yield, right? We probably will not really call that this structures has really superior photoemission properties.
Can I ask a quick question?
Uh-huh.
So, how come zero concentration of beta-mercaptoethanol actually changes over time, the quantum yield? What makes it change if you don't add anything additional to the system?
I think just over time the quantum dot degrades.
Okay.
Yeah.
So this is degradation in that short period of time, 100 hours?
I believe so, yeah. This is why
I don't think the quantum dot degrades. The quantum dot probably is staying there. So the chemistry on the surface is changing. You create entrapped states and it becomes not luminescent anymore. It's a quantum yield change. It's not showing anything about really physical degradation of the system. The quantum dots are very stable structures. They not degrade just because you wait for 100 hours. Right? So it's changing the quantum yield. So it means something happening with the ligands on the surface. There is a chemical reactions. Maybe they disattached, maybe they deprotonated, maybe they react with something else in the solvent, who knows. But something happens during this time so that their quantum yield decreases, probably due to the presence, like more trap states appearing after, I don't know, 10 hours, right? You really, maybe because the ligands disattaching from the surface.
Mm-hmm.
There are some dynamical processes, and again, this plot, of course, not answering the question why and what. It's just
Right.
a matter of fact that in all cases, even in a case when you have whatever your beneficial concentration for having some quantum yield increased from 30 to 50 or to 60, right, twice increased comparing to the zero concentration, the black line. It's not really staying constantly, how say, yeah. So I think it's they call it photo bleaching, or well, you can call it photodegradation, technically, right? So it means degradation in the sense that optical properties degrade. The system by itself stays, of course, as it is. I don't think that your quantum dot just becoming not a quantum dot after that.
Right.
It's a
Strictly the
chemistry
surface.
on it's a chemistry on the surface is changing.
Mhm.
And it's a really very interesting question to answer why, and that's why actually you are doing research.
Yeah, that.
Mainly to answer the question, not because science really provide these superior properties. They maybe not, but although they have some potentials, right? It's showing some potentials, but it also having this problem with reduced quantum yield. So knowing the mechanism, understanding what's really going on, helps us to first explain this behavior, and maybe then we can find a way to fix it, so it will be not degrading after, if we can treat it accurately or can control it accurately.
Yeah.
Okay.
I have nothing more to add to that. But that's like the reason that I was starting to do my research on it. Was because it showed some sort of promise with an increase in the quantum yield from thiol. So yeah, but clearly too much of it doesn't help anything, and not immediately, but over time makes it have no quantum yield at all. So okay, then there's a small step that I have only worked with cadmium sulfide, so I do not know anything about any other quantum dots that aren't cadmium based. But it threw in there something about how okay, sorry, 1 second. A quantum dot, like an IMP quantum dot, capped with topo has less than 1% efficiency, but then capped with thiol have 30% efficiency. And there was a study I didn't.
Is it also from this review paper? This
Yeah,
information?
it was just a small paragraph at the end, which is
And again, they refer to some original work, right?
Yeah, they do, and never mind. Yeah, but I looked at that paper, and that was significantly older, so I was gonna go and look through all of the different types of papers, but they're just very hard to find. Not find, but just read. So
Well, yeah, that's why the rule is not use the review papers for this type of presentations, because instead of one paper, then you have to prepare 1,000 papers which were cited already, right, to answer all these questions if people start asking you questions. Because in a review paper, this is really done just statements.
yeah,
But the main question for research for scientific papers, it's not really just the statement, we need to prove it, or we need to see the proof. Like I would say, you have the statements and there should be a graph, same as it was in your previous slide, with some experimental data showing that, yeah, look, emission is increased by 30%. Here is a peak rose, here the peak goes down, or something like this, right? But it's not it's a problem with the review paper.
Yeah.
So be careful. For this type of presentations, it's not really the best choice, but okay.
Well, anyways, my review of the paper itself, it's a pretty good paper, but there's some inconsistencies with what it's talking about, because it'll be trying to make a point and then it'll jump around and it won't finish what it's trying to say. So I had to do a lot of digging, but all in all, if you're trying to learn about any sort of how capping of quantum dots works, this is a really good paper to look at. And it talks a lot about how the benefits and the not benefits of capping it, of capping a quantum dot, the different kinds of quantum dots, not only cadmium sulfur, because that's more of a new, not new, but it's kind of starting to be used more than, but a lot of papers are focused on cadmium selenide. So anyways, and then it has a lot of information about surfactant, I don't know how to say that, but exchange, which I knew nothing about. But if you're interested, it does have an entire, the entire second half of the paper is about that. So if you want to learn about that, that's a great place to go. So there was a statement made, and I was hoping somebody could clarify it, and I really wish I had brought my paper because I was gonna read the sentence that it was on. But it was talking about how the difference between monodentate and bidentate thiols, and I looked it up, and bidentate has 2 sulfurs on it, which they're just connected with a carbon, so there's a carbon and 2 sulfurs.
Then it's not a thiol, right?
Yeah, that's what I was thinking, so like I don't understand what...
Brandon, am I right? We call thiol which has just 1 sulfur.
Right. Yep.
If there are 2 sulfur, how you call this compound? Like carbon and then 2 sulfur attached. Levi also should know.
I think it's a bicarbon. No, it was the stuff. It was the title that we used with Andrea. Bicarbonate, I think.
Okay, well then I'll look that up because that did not make any sense to me. So anyways, that was something that was inconsistent through the paper. And
So in other words, you find the typo in this paper, right? So
well,
like technically they should not really use this language.
yeah, it was very confusing. And then they just like ended the paragraph after that. So I was like, all right, I don't know what's happening. But I thought that maybe someone would know, but he wasn't really looking at it. So, and then I just have one. So this is a paper that talks about this ligand being passivated on the surface. Again, I don't have any of the specific information on it, which, you know, second thought I definitely should have. But so a preformed cadmium selenium quantum dot, which is not particle, I just put that, was introduced to thiol, and like this particular type of thiol, and a single thiol, this kind of thiol, quenched emission by 50%, which was very confusing to me because why would that happen? But this is the explanation that they gave for it, was photooxidation of the ligand occurred creating disulfides resulting in photoinstability. So if anybody can help me out figure this out, that's the paper. I don't understand it at all. So yeah, anyways.
Well, this is just saying photooxidation of the ligand that's saying that you have the thiols creating disulfides, and disulfides is actually a sulfur-sulfur bond.
Okay.
So is it actually removing some of the surfactants by turning them into disulfides, and then the sulfur is interacting with another sulfur, and therefore cannot interact with the quantum dot?
Yeah, I guess again it's a process what happens on the surface, so you're losing your ligands, right?
Right.
And that's again of course creates trap states and probably results in a quenching. So some chemical reaction is happening there.
So why would the loss of a ligand be detrimental when a quantum dot just in a singular solvent can be
Do we have dangling bonds? What is a dangling bond?
I'm assuming just a not saturated bond. But
Okay, not saturated bond. If you lose ligand, right? So what happens with a bond where it was attached to cadmium? It's having this non-saturated bond. Pretty much the same. It's not as strong as if you see in organic, like when you have radicals.
Okay.
Take benzene ring, disattach hydrogen, you will get a radical, whatever is the name of this radical. It's extremely reactive. Its properties very different from a regular benzene molecule, because of this dangling bond, not saturated bond, right?
Mm-hmm.
So pretty much the same story with a quantum dot. You having the difference is of course because it's a different nature of the bond. It's coordinated bond rather than covalent, like pure chemical covalent bond in carbon hydrogen kind of type of bonds. But you have cadmiums which are in a bulk structure. Bonds would like to have 4 neighbors, right? So they are 4 coordinated cadmiums. On the surface, if you not having ligands, you might have only 3 neighbors, you might have 2 neighbors, you might have only 1 neighbor, which would be making this cadmium extremely reactive, right? So that's why it will react with everything which is surrounding, if there are ligands, whatever, solvents, oxygen or something, to saturate these bonds, right? And if you're not controlling it, some ligands like oxidation processes usually not doing good things with optical properties, right? So same as you saw with your thiolate. Like if you have a thiolate, you have your lowest transitions really associated with this orbitals just sitting on the thiols, not dealing with the quantum dot at all. Of course, they're not luminescent. Of course, you're losing your luminescence. If you just just lose proton from the siles, and you have many siles on the surface, right?
Okay, yeah, that makes a lot more sense. I was very confused, so.
So in your structures, when you work with this small Cat33 selenium 33 or Cat33 sulfide 33, and we don't put ligands on the surface, right? We optimize, and we still, if you look on the absorption spectrum, the low states are optically bright, optically active, right? The question is then, oh, why it's optically active? Why are we not seeing a quenching? Well, because of the reconstruction of a surface. Again, if you look on your structure, you can see how much it changed compared to the bulk. So you have really changed, and like your cadmiums on the surface is really different. The bond lengths, cadmium selenium or cadmium sulfide bonds on the surface becoming longer, comparing, and they shortening in a core, and they elongating in a shell. So this surface reconstruction change in the geometry kind of compensate for these dangling bonds.
Okay.
They kind of heal themselves.
That makes sense.
Right? However, it's a very rigid structures. So we were taking really 1 nanometer quantum dots. You have just one, number of atoms. Like the size is so small that they can really move. Now, if you put several layers, like you start with this, then you put layer of Cat selenium here, then another layer, and like 3-4 nanometer quantum dots, right? Of course, the surface becomes much more rigid. It cannot, like your core is heavier now, right? It cannot change the length of the bond lengths in the core as easy as if you have just 12 or how many atoms in your structures, in the 1 nanometer structures. You will have now thousands atoms in a core, and even more on a surface, right? So then if you go to real size quantum dots, the surface reconstruction cannot take place as efficiently as it does in a small quantum dots. So small quantum dots behave more like molecules, in other words, right? And molecules can adjust their structures very easily. The bulk solid materials, of course, much more rigid, and they cannot make these changes in the geometry as easy. So that's why 1 nanometer quantum dot have these self-healing properties, while 2-3 nanometers will be not able to solve this problem with the dangling bonds. And that's why loss of a ligand from bigger quantum dots will have much more serious effect comparing to your structures which you model, right, with this 1 nanometer structures.
Yeah. Okay, that makes a lot more
But in both cases, the source is dangling bonds, right, not saturated bonds.
Mm-hmm.
And the question is how you separate them. If you separate it kind of in the right way, then your optical properties are improved. If you put something there which is really creating this localized trap states, then it's not helping, and the emission is.
Okay. Roughly. Anyways, that's it.
I just want to point out Levi's extreme athleticism to be able to hold that form for this amount of time.
Somehow you are freezing.
You may look.
We're not frozen for either of us, because Braden's in the same room, and we can see him moving on our computer, and he can see us moving, so NDSU is the only frozen point.
You're seeing through the video point photo.
But for us, you are freezing.
Right.
Oh, maybe we still have questions to Alisa. You kind of disappeared so quickly.
I didn't think
It
I
was
think
a
they
trick.
would have asked them.
Any questions?
In a review point, the last line you said,
Just put it to the.
contradicting information about Thiol.
That was the last slide.
So can you give some information? I mean, example? I don't know what you think. What is the
Because I
contradicting
didn't
information?
understand what that was, and they didn't explain it
There is an
very well.
advancer.
So this was saying that it went like the definition, and I was like, didn't touch out all of the benefits of Thiol, and I was like, that doesn't make sense.
Is it because of concentrations? Because that figure you
Well,
show,
it's technically not only concentrations, it's also just different groups reporting different data.
because the paper,
Some showing increase, some showing decrease.
the figure she shows the, line, they are concluding that that's changing because of thiol concentration, change the thiolate concentration on the surface, and that changed the
The properties, yeah.
properties. Yeah.
And they again, they make the conclusion, this is not actually was included in her slides, but in the paper they also, to prove that this thiolate, they change the pH. So they really kind of artificially
Yeah.
deprotonate the sial, and then they clearly see the quenching of the emission, which kind of showing that you have this quenching probably due to the presence of thiolate instead of sials. So that was all very nice. But actually, there are like different processes, different groups report. In some cases, it's decrease. In some cases, increase. So it's really not very consistent. Clear ideas what's really going on with sials there.
And the next presenter is Dr. Dayton John Fodel.
Okay.
So in your case, it's a research, like you will be talking only about your data, no paper presentation.
About my data, well,
So you take responsibility about it.
Yeah, so it's a really kind of research of our
what
team.
I'm doing. Yeah. Yep. So I'm going to be talking a little bit about the electron dynamics and charge transfer in our CAD33 Solid 33 with a black dye system. And so this was a system originally created by Peng, I don't know, 3 years ago?
Who knows, maybe 5 years ago.
Yeah. And so,
Long ago.
and so he applied surface hopping dynamics that Dr. Kalina's group is familiar with. And so I've been taking a look at some of the data and running it through our Redfield theory dynamics. And so we're going to take a look at a few different things in terms of binding with the dyes to the quantum dot and how that's going to affect the overall charge of the system and how that plays into the electronic structure and eventually the dynamics. And so, you know, the main reason that we're doing this is, again, we're interested in absorbing some form of light into the quantum dot, have an excitation, provide some type of charge transfer so that we can then do redox chemistry either on the surface of the quantum dot or on the dye itself. And so in this case, we're primarily interested in how the whole is transferring from the quantum dot to our dye molecule. And so this is a system, and this was an image I just put up in VMD. So this is going to be our quantum dot system here, and this is our black dye system. And so you can see this pink atom kind of in the middle is a ruthenium atom, and then you have thiocyanate groups, 3 of them.
Technically, it's not atom.
Well, it's a metal organic complex.
It's an ion.
It's a +2. Yeah. It's ruthenium.
It's important.
It is important. And so one of the main things that I've been trying to decipher going back through Peng's data and with some of my data is how this carboxylic group is attaching to the surface of the quantum dot. So you can see normally you would have one of the oxygens be protonated on a carboxylic group, whereas here if you have a bidentate ligand, so both of the oxygens are binding to the surface of the quantum dot, you're deprotonating.
2 different cat groups, right?
Yes.
Like each oxygen.
Yeah, not to the same. Yeah. And so to 2 different surface atoms, and with the deprotonation of that hydrogen atom, there's still the negative charge that gets kept on the system. And so one of the issues we were looking at was a closing of the band gap, and how does accounting for this type of charge help or hinder?
Oh, before you go to the charge, everyone understands what's the charge on a ligand here? On a complex, right? Quantum dot, of course, not charged. It's having even number of cadmium 2 plus and even the same number of selenium, right? Selenium 2 plus. But do you see the charge on a metal organic complex? So ruthenium is 2 plus, right? Trees, how it calls, trees.
The thiocyanate groups.
Yeah, they are neutral, right? Well, no, trees pyridines, so how they call it. Like the ring guy.
Yeah.
So then it is a neutral ligand, and then isocyanides, 2 of them having, each of the isocyanides having the negative charge. So technically, if you don't have carboxylic groups, right, so then it has to be neutral, because you have 2 minus due to the ligands, isocyanide ligands, right, and 2 plus on a metallic on a ruthenium complex, neutral. But then when you put in the carboxylic or carboxylate groups, if it's deprotonated, then we have a negative charge, which is due to the lost proton, right? And then this charge probably really should be originated just through this carboxylic group, should be localized on this carboxylic group, if our calculations are correct.
If they're correct. And so, yeah, so we'll go through some of the projected density of states. on these systems. So the first thing I'm going to show you is these are the partial charge densities for this system. And so I've listed, these are going to, on the left are going to be occupied states, with the HOMO being state 391, and on the right are unoccupied states being at 392. And so you can see that the states closest to the band edges, both in the valence band of the occupied, you can see that they're localized primarily on this dye portion of our system. And so that's what we're looking for. We want the hole within the valence band to travel up and generate inside the quantum dot, and then have a charge transfer event so that it ends up being on, spatially separated from the quantum dot and being on the dye part of the system. And so again, in the conduction band, we want the opposite. We want the electron that's photoexcited to stay on the quantum dot portion of the system. And so you can see the four lowest bands, at least that I show here, have their density localized on the quantum dot portion of the structure. And so yes.
So does the initial geometry matters? So
Matters for what? For this type of orbitals.
Oh,
yeah,
so you're saying that if like the die was kind of bent over and you'd have like pi arrangements?
Yes.
So yes, I would say it would matter because you'd have different varying levels of interaction. But in this case, this is the way that they're organized. This is going to be the initial geometry, and so we know that there's going to be.
This is optimized geometry. So there's really, if it's creating a bond, right? So there is not really a lot of like if you change the question is, you thinking about just changing the angle, right? So then I would say it's probably pretty much optimal angle. It's very rigid because the structure of the die has to be octahedral, right? So you don't have really flexibility to change the structure of the die. So that's why the angle is really kind of fixed. It cannot just be completely flat or like that. Of course, it deviates a little bit, and when you do dynamics, you probably will see how this bending angle is changing.
Yep.
But it's really very small effect. Like you're not expecting that it's completely laid down parallel to the surface or something like this. It's pretty much perpendicular, and it's due to the rigidity of both. Of course, quantum dot is very rigid structure. This one is kind of rigid due to this octahedral. You cannot really change the angles of the bonds, because then you will lose your octahedral structure at that moment, right?
Yep.
If you're talking about how these things will be affected by placing this ligand or this dye on a different facets, let's say not to the bottom but to the top, I think we don't have the answer, right?
No.
We didn't try.
No, I mean there are, well, and part of that was, briefly looked at, but inside, so the bulk slab of the CAD sulfide, then you cut out the quantum dot portion of it, you can see the different layerings of the system, and so there's a little bit of a different surface reactivity in them, but this was kind of what was decided as this is going to be the best fit. And so same thing, because you have these two oxygen atoms from the carboxylic group binding to the surface, it's also going to take out any other type of play, even at the anchor group, that might have some type of rotation effect.
But what we did in the previous studies, not with this complex, but with ruthenium bipyridine complex, which is very similar to this one, but with neutral, there's no isocyanide groups. So protonation, or like trying chelating, like attaching it through the different modes, same facet, same surface, right? But attaching not to kind of to the same cadmium, to monodentate one cadmium, and actually even protonating, putting the proton on a not really changing this. HOMO is always on a die, and LUMA is always on a quantum dot. Well, I would say LUMA is not always on the quantum dot.
For the
it might be on a die as well, but HOMO is always on a die.
Mm-hmm. And that's the most important piece, just to have the charge separation.
So what controls for LU being on the die or on the dot?
Oh, I was wrong. What controls the charge on a ligand?
Okay.
Not on a carboxylic group, but charge on the actual ligand.
Mm-hmm.
So because we have in this kind of shift
Mm-hmm.
between the orbitals from the die versus orbitals on the quantum dot, so they kind of too much stabilized if you have neutral ligands comparing to the quantum dot states, and they becoming less stabilized or more destabilized, means they're moving, and then they kind of introduced to the gap of the quantum dot, making HOMO being on the die, right?
Mm-hmm.
If we have negatively charged ligands. Like we checked it. We changed isocyanates by chlorines, and it was pretty much the same electronic structure.
Right, so if you think about like the wedge and dash, you. Oh, they can hear me? My
We
bad.
can hear you,
Sorry.
yes.
Oh.
So in other words, this energy alignment or kind of origin of these states is much more sensitive to the type of the dye by itself rather than to the geometrical features. How is it attached, what's the linkage group, and what's the surface?
And so,
Can I ask one quick similar related question? Does the presence of the quantum dot change the structure of the complex itself?
not
So, for example, it looks like in this particular figure, or in these figures, there's that cyanide group almost looks like it's taking something that would deviate from an octahedral orientation in the complex.
I guess it depends. Like it's a two-dimensional. Like if you were looking at the 3 dimensions, it's octahedral, right?
Yeah.
It's preserved. It's octahedral structure.
It is okay.
yeah.
It just the projection due to this 2D.
Yeah,
2D
I
figure.
could turn it around a little bit. It would look better.
Okay, gotcha.
Yeah. Okay. So one of the things that we were interested in is, well, so I talked about putting this charge on versus not, and trying to compare what we had versus what we can get. So in looking at two different ways, so I can take that whole system, and I'm not going to mess with the number of electrons. I'm just going to put the system in. I'm going to optimize it. I'm going to see what I get. And so doing that is what I call this no charge.
So it's neutral. Although you're supposed to have minus on a carboxylic group, but you assume that there is no charge.
Right. So I'm not adding any charge to it. So it may be that, it's not quite correct, but I haven't added any charge to it. It's just what the system can calculate. And so that's what this no charge is. And so it also corresponds to the blue in this density of states plot. And the second thing that I did was I added this extra electron that we're assuming comes after deprotonation of the carboxylic group. And so that's what the 1 electron, the red density of states, and then I'll talk a little bit about the absorption here and then on the next slide. So in looking...
Before you go, so this is done with optimization of the geometry with these different charges, or you just put a charge without changing the geometry?
So these ones were taken as, so I have them both. I think these ones were the single point calculations, but I have them optimized with and without.
And I think you also have orange.
If I have orange, there's not supposed to be orange.
Am I the only one who's seen orange?
Does it look orange kind of down here?
No.
I think where the red and purple overlap.
Okay, so yeah, so when I turn down the transparency on the red, maybe that's why it looks a little different. That way you could see them overlap.
I see. When it's covered with blue, then it's kind of more red.
Yeah.
Okay.
Yeah.
That makes sense.
So yeah, so the blue is just the neutral system, and the red is with this additional charge that we're assuming is there. And so you can see, there's a shift. Let me see if I have it right side. Okay, so this is the two of them separated. Can you guys see? Anyways, so let's go back. So there's a shift in terms of where the energy levels are, almost as a relative in between the blue and the red, but you're still going to see, so here you can see a slight partial white space. So this is one of the things that I've been trying to do is get a complete convergence of the electrons in single point runs and optimizations, because it's not like everything is filled to 1 or 2 electrons. So I mean it's very, very close, but it just is something that I haven't gotten to yet.
But your gap is open, right?
The gap,
in both
the gap
cases,
here,
the gap is
yes,
not
is
zero.
not closed, right? Which is good, and that's what we're looking for. And so that's one of the things I'm curious about in terms of what we looked at earlier. So the features are going to be very, very similar. You're going to see lower density of states here at the bottom of the conduction band, whereas the valence band is going to be very dense, and that's going to play into looking at relaxation rates and what might that lead to.
John, can you show by your pointer the valence band top?
So the top
Yes.
One case
in
and
both
then
of
the
them.
second
Okay.
case.
So in
Mhm.
so for the neutral, this line here is going to be the top of the valence band, and for the charged, I mean it's
So
basically right at the edge of
the field area doesn't go up to black line there. Is it
just slightly.
is it deficiency of plotting, or it is a true occupation below 1?
Occupation.
So it is p-doped, like
But
missing.
your back
Slightly,
gap,
a little bit.
what is it? Like it's
Right,
around
right,
1
so-
electron volt, right? Or
Mhm.
half
So
of
here-
electron volt.
Yeah. So
At least.
here so this is this will be cleaner. So this is just one of them. So this is
With the charge?
no charge.
No charge.
This is the one with the charge. But they're very, very similar. So yes, you're going to get, an open gap, whereas this one has something similar towards the top. And I'll talk about that a little bit later, because when I was looking along the dynamic trajectory and doing these PDOS, where the Fermi level would vary between, two different states depending on that partial occupation. So ideally there's going to be an open gap, and I believe that it should be filled. It's just that where the Fermi level is relative to the calculated energy states, it has a partial occupation just above it.
But again, we don't have this even small deviation here, right, from your completely filled versus partial filled population, right? We don't have this problem when we put a negative charge, as it's supposed to be, right?
So then
Like then your black and red completely.
it's very, very, it's closer.
Side.
So with the additional charge added in, it's going to push the Fermi level up above
And you have-
any state that
and
has
then you have a
population
pretty
in it.
distinct kind of here.
Then
here is
this is it.
occupied, this is unoccupied.
Right. So
Okay.
instead of having 0.7,
between.
it's going to be 1 point something. So it's going to be a higher occupation. That's kind of the cutoff line in VASP for how it does that. If it's above 1 or less than 1, that's where the Fermi line cuts off. But I still want to talk about in the last slide. So looking at this projected density of states. So this is solely for. I got slid a little bit. These are relative percentages on the atom types for the HOMO orbital. So with this no charge, you see the bulk of the orbital population is located on the selenium atoms and on the cadmium. So that would signify that they're supposed to be on the quantum dot instead of being on the die like we looked at in those partial charge densities. And so with the 1 electron, then you're seeing a reduction in the selenium occupation as well as the cadmium occupation, and you're seeing the primary localization on ruthenium, the sulfurs, your nitrogens, and your carbon, so on your actual die portion of the material. So I think that gives a little bit of a clear indication on which way we need to go if we need to have our occupation of the HOMO on the die portion of the material. So adding this charge into the rest of what I'm doing is what I'm working on currently. But that was just kind of taking a first look at this and saying what's going on with and without the charge.
This is absorption spectra on the
And
right?
these, yep, and so I'll show this, I know I have another slide in comparison with what Peng had for his. So in terms of our absorption, so this no charge system again is here on the red, and the added electron is the black absorption. And so by providing, this extra electron to the system, now you have a filled occupation level. And so when we're calculating our oscillator strengths and our absorption values, you're not going to see this small red curve here being some type of artifact saying we have an empty state that's not really empty right at the edge of the valence band. But looking at the main spectral features, you see.
But before you go there, so I kind of want to return back to Dmitri's question when you said like it's a p-doping, right? You said like, looks like it's a p-doping state, right? When we not put in the right charge, it's really like we dope the system, well, p-doping because we lost the electron. And that's why this level really behaves pretty much the same as we
Yeah,
just
almost,
take cat
almost like a
selenite
small trap state
make
red
it go.
digit.
Oh, okay, nice.
Yep. So I mean,
Which also kind of a note, especially related to the kind of a little bit related to what Alisa was presenting, right? So we can say about that there can be quenching of the luminescence or any kind of change in the dynamics due to the changes in ligands, like chemistry or attaching, disattaching of ligands. It's also possible of charging, recharging, which might be just a charging through the solvent again or something, right? And that's why this kind of artificial behavior might be really kind of just, we can think about, yeah, it should not be there in ideal case, but technically it might be some modeling of the model with extra charge, or kind of, in our case it's positive, like I say, it's neutral means we lose an electron, right? Which can be also used as a formation of the defect, and again, affecting the emission and affecting the overall optical photoexcited dynamics, right? So overall, I think we still can use this data, but just we need to interpret it in a way that suppose that we charge the system, means in our case it's becoming neutral, which means it's not in the right balanced charge. So it's adding this state, which is kind of doping, very analogy to the doping associated state, and yeah. Well, social spectrum also a little bit affected, especially in the lowest energy states.
Yep. And that's part of it too, because you can, more or less make the assumption that it should be charged. It's not hard to go back and just artificially implement that for the remainder of, just saying where the valence band edges. Mm-hmm. And so, in looking at the features, so I only plotted it out to 4 electron volts, which is just going to be, right at this major peak here in this graph. But when you're comparing the charge and no charge systems, you can see that the features are very, very similar in terms of shouldering. There's a slight redshift, in your neutral systems kind of coming off of here, but it's not major. The biggest thing for me was in looking at where these major peaks occur, primarily very, very close to 2, and then here close to 2.5. Is making sure that they compare with these major peaks, which are calculated out as a quantum dot to quantum dot, because we want the quantum dot to be the photoactive material. That way, you don't necessarily have any type of photodegradation to the dye material that's on the quantum dot surface. And so, this quantum dot to quantum dot, major peaks are here, coming up just shy of 2, similar to these here as well. And then you have another major peak set here, close to 2.5, and then the relative intensity isn't quite as high because I didn't take into account every possible transition that might occur in the quantum dot, but the same shaping is here as well. And so that's what I was looking for. And then again, here just below 1.5 EV, you do start to see some of these smaller absorption peaks that correspond to some of the dye to quantum dot or quantum dot to dye within the system. So overall, fairly happy with at least the shapes and where the transitions are coming from in relation to what we've had previously.
So the bottom one, it's again for which system you have in the bottom?
So this,
it's punks, right?
Yes.
Results. So probably it's also with this zero charge,
right? And so
lost electron.
Part of me
system.
Right. Part of me was wondering if it's just a blown up portion of what the static quantum dot, this lower energy portions are. Yeah. That's just here. Okay. So I wasn't really. I want to.
I guess it's literally red and black lines from this curve.
Which is up here.
Dye to quantum dot and dye to dye.
Yeah. So that's what I'm assuming there.
So the left panel is for no charge system.
Mm-hmm.
Why there is no absorption in the zero?
This one here is what you're talking about. That's a good question. I don't know if it's something, because it looks like it cuts off here. So I don't know if he didn't go below something like this. He might have stopped it, or depending on the Gaussian broadening.
There is some feature in the 0.5, right? So it's kind of like it's not 0, right? It's 0.5 electron volts where he's seeing this peak.
0.5 is right at just, it looks like it starts just after 0.5, so I don't know exactly. I'll have to go back and
also your spectra is just a single point, single point, and this one is it also, or it's averaged over several structures from the dynamics? Do you know?
That's okay. I'm not sure.
It was not in the paper.
Yeah. Well, when I was looking at, because they were separated figures and paper. Most recently, I was looking at the captions.
Technically, because the features looks very similar to yours. Probably it's a single point as well.
Yeah.
But this one is for TDDFT, right?
Oh no. It's VASP calculations.
So he did.
It's
Yep.
how it calls single particle spectra.
So yeah, he did both VASP and he did some Gaussian, which I haven't added in, but I also have some of that to compare with. Just.
But this is for sure it's a VASP then.
Yeah. Yep.
For his system.
Yep. Okay. So in the last couple of weeks, we've talked a lot about our methodology and the steps that we take. We do ground state calculations in Gaussian and in VASP. We look at what the energy levels and how it's the charge is localized on the systems. And then we talked about molecular dynamics and how now we're moving our atoms and how that changes the energies in our system. So this was, well, these are the energy levels. So these squiggly lines going horizontally is one Kohn-Sham orbital energy across a little over a 4,000 femtosecond trajectory. So this is something I've been trying to make sense of and use it for where my orbital range is for our calculations. So when we were looking, we found, looking at the Fermi energy, you're looking at it almost right between two very, very tight states.
But this is with incorrect charge.
Right. So, I mean, it's hard to say how big of a difference the single charge would have on a dynamic simulation, but I don't know if it would be drastic per se. So that's just one thing that I don't know if I'm going to run just a short segment of it charged and do a comparison and just take a look at it.
Just to see whether you will be able to
right.
Well, although your ground state calculation shows very similar band gaps, right? But you have a very different shift in the Fermi energy, right? As you said, like you have almost completely, not a problem of half-filled orbitals when you have a right charge.
Yep.
And this probably would be already good enough to kind of maybe split them.
Right, and so, but this also raised another question, because so this was the energy file that came with all of his real or coupling files in the directory. So this was in the figure another fluctuation part or plot of his energies, but here you can see he put, so they're shifted to have the Fermi energy at 0. That's not what I'm looking at.
He used how it calls the Caesar operator, so kind of artificially just.
Right, so now he has this large band gap, and where he puts the Fermi energy, which doesn't match where the Fermi energy is calculated out to be inside this system.
So he just kind of used it randomly, like in other words, his home, like in your case, yellow is your HOMA,
right, so
backward, blue is your HOMA, yellow is your NUMA.
So if you're looking here, I mean, you could basically kind of split it out. But the other thing I was thinking about was, so you look at, you have this range from -3 to -5 electron volts and how sparse some of these states get. And you think back to how the valence band and the conduction bands look. You have the conduction bands having, a much lower density of states.
Because they come in. Are they coming from the quantum dot or from the
so
band?
these are from the quantum dot, right? Compared to this valence band edge, which is going to be very dense. And so part of me is curious about where these fluctuation energies are coming from, because to me it would make more sense, because you'd have, the severely dense population of states be close to the valence band, and then the top of the conduction band is going to have, a few more of these states that are localized on the quantum dot. So that's.
We need to put a charge and see how the dynamics goes.
Yep.
Because it's again, if we're thinking about p-doping, this is really maybe the states originated from the p-doping on one hand. On the other hand, these states, if they come in from the dye, right, so they are sparser, of course, then like in other words, your gap for the quantum dot would be between this, I don't know, this dense band and then around -4 or something. And these sparse states probably coming from the ligand, which of course we expect they have to be more splitted, more discrete.
Yep. So yeah, so we'll run a short segment and take a look and see once how they overlap and see if you can actually get some of that opening. And from that, we can decide if what we want to do with it in the future. And so that's the main reason I had this image in there was, you know, just to look at the comparison of, because I was looking at both of them, took me a little bit to figure out kind of what was going on with why he
But
all of a
how
sudden
did he define, like, where exactly he applied the scissor operator? Was it applied between this yellow and blue line, or between some other lines?
To me, it looks like it's up above a little ways.
So he kind of, this blue line stays in a like.
Right. So it almost looks like it was here or here. So, and that's part of why I'm curious if he had a different energy outcome from something that I don't have.
Here we have, of course, because we treat electrons and holes separately when we do dynamics, right?
Mm-hmm.
And then kind of taking out the unoccupied levels and call them occupied. They have different nature, like, you know, all the dynamics will be affected completely, like, pretty significantly.
No.
I mean, for electrons, using these levels and call them holes, and for electron dynamics, it just means that he having the relaxation to the, not to the luma, but to somewhere kind of in the main band, right? But for holes, it really looks like we are pretty off with low state kind of dynamics, because it's completely different nature of these orbitals. And again, another problem with this, so like people who work in with VASP, you know that we cannot trust the band gaps if we use the PBE functionals, or whatever your functional, pure GGA functionals. So because the band gaps are underestimated, so they are smaller than it's supposed to be in the real systems, right? And that's why even closing these gaps is definitely the artifact of the functional. If we use hybrid functional, then the gap probably will return back to 1 electron volts or something, right? And we will not, even with this charge system, and we will not have this problem at all.
Yeah, and even in the HSE calculation that's running, you can see that it's starting to open up.
Oh, you start already?
Yeah, well, when the power went off, it was in the middle of the calculation, so it kind of reset. But looking at the other car files, the state distribution, it looks like it's... So yeah, so that was, this image was the main reason I put this one up there. We may talk about some of these figures a little bit later, but for right now, we're gonna, so kind of move on. So in terms of, you know, looking at the dynamics, we were interested in how the density of states and where the charge is being localized changes along this dynamic trajectory. And so this was, I mean, this is just a video of a density of states that, you know, taking it every 100, well, for the first picosecond, let's see if I can do that slower, every 100 femtoseconds. It doesn't do it that way. But you can kind of see in this system, you have
Too quick.
It's really quick, but you have, you know, almost an overpopulation in this. And so that was, that's partly, I think, along the dynamics, you have some stretching of bonds, you have some, you know, bond angling being shifted due to this atomic motion, and also improper charge on the system. And so you get a unique density of states that I don't think is necessarily correct, but we're working on going back and recharging it the way it should be done, and we'll see once how this comes out.
Here you feel like this occupied states, this is based on your, on the Fermi energy as it is calculated by VASP, or it's based on the way how Pan was using his scissor operators?
This is the way I calculate. So there's no scissor operator enacted here.
So again, so your low state is half field or close to half field. That's why again your black line and the covered line is not exactly coincide.
Yeah. So if you haven't caught a theme, correct charge is kind of a big deal. Okay, so this is kind of what there's a lot of information. So the axes, X is time in femtoseconds, Y is a population percentage, and then each one of these colored lines corresponds to an atom type. So this is just the PDOS.
But this is for which level?
This is the HOMO at a number of different time steps.
HOMO based on the Fermi energy,
yes.
Right?
HOMO based on the Fermi energy. So
John, Why did you took this sparse steps? Are you confident that nothing interesting happens in between, or you just got tired to plot too many points?
Well,
By the way, is it how it was calculated with this? Like we have in what's the port team for calculation? What is a step in a time?
this one.
5 or less?
Oh. Well, so in terms of what he did for dynamics, I'm not sure. I don't have his in-car.
I think. Okay.
So
So it's actually your choice of this.
yeah, so I took it every 100 for the first picosecond and then every 500 for the rest of the trajectory. So part of it is I wasn't sure how we were charging the system, so I didn't want to just burn through a ton of resource and lock everything up. So I took a sparse density of this. So I'll go back and do this. I've got a script ready to run every femtosecond, but maybe we'll only do it for like 100 or 200 and see once how it goes.
But it gives you just more smooth lines, nothing else, right? So you still will have this, like,
right.
such a
It
big
just has
deviations
something.
definitely will stay, right?
So it will be exchange of population between orbitals of the same symmetry. Like
If you look on the 500 and 1000 peak,
It's probably due to the.
if we connected this two peak, it will get a shape of the like letter on 2000 feet.
What? What?
I mean, if we look on the 500 to 1000,
From here to here.
they have a spike, right? Yeah. But if we get calculating every 500, then we will get only the
Really
high
large.
peak. Yeah.
But this is probably depends on this again, how close the luma is, right?
Yep.
Again, this yellow,
And
bluish lines, sometimes they come much closer,
Yep.
sometimes they're a little bit
And
more
that's-
splitted, and probably at higher, at longer times, you have a little bit increase in splitting,
Yep.
and here they really kind of almost degenerate, and that's why you have this.
And that's a
Switching.
huge part of it. So in looking at where the Fermi level
But-
cut off,
Is it, again, same as in your ground state calculations? So what is supposed to be luma is a quantum dot state, or not?
it's supposed to be die. So the luma
Wait,
should
die?
be quantum die.
Oh, the luma
The
is
HOMO
quantum
should
dot.
be
HOMO
die.
should be die.
Yes. And so the Fermi energy oftentimes was right between where there was full occupation and partial occupation. And so it would do that. And so that's why you're seeing, so this top line here is for cadmium, right here. For selenium, it's kind of a brown. And so you can see that there's a very drastic change in where it's happening because it would jump in between those states for what is HOMO and what isn't. And so it would shift it from the quantum dot to the die to the quantum dot to the die. And that's why you'd see these really large population percentages on the quantum dot at certain time points along the trajectory versus, these points in between here are localized on the ruthenium and the sulfurs, and you've got, your nitrogens creeping up here as well. So depending on how these occupations are happening, and this is just all done with the neutral charge, so putting that, extra electron on there should smooth it out, and we should be able to see a more consistent basis for a HOMO population will be almost entirely localized on our die versus
And what again is the green one?
the green one is ruthenium.
And the blue or
The
black?
the blue is for sulfur in here, and this brighter blue is oxygen. So this is these points kind of right through here.
But your carboxylic group, is it contributing? Like carbons and
So-
oxygen from the carboxylic group?
Yeah, so you're gonna. I mean, the oxygens don't have a ton of charge on them. That's this brightest blue line on the bottom, and then the carbons are this darker blue
little
line
bit.
kind of through here. Yeah. And so that's what it's looking like. So when we're talking orbital indices switching, it's happening because there's an artifact with actual
The just degenerate
populations.
state. Yeah.
Right.
We
And
don't
so,
actually have the gap in this system,
Right.
in other words.
right. Yep. So going back, we'll go through all that again. And, with the
But
charge
for
states.
sure, like you can see, like you need at least the first 1,000 where we have this a lot of
Mhm.
things happening, right? So I would suggest would be nice to run with a charge and see the dynamic, and then kind of do the same analysis and to see how this picture
Will change. with
changing
that.
or maybe
Yep.
also fluctuating
Right.
if you
And-
have the right charge being on a
Right.
carboxylic.
And ideally, it'll be almost exclusively like this with, minimal occupation. Or like when I showed the PDOS on the very first NC State slide, you see a large for the no charge and not.
And another approach, because again, we have this problem due to the functional, right? Because again, if you use the hybrid functional, even with the wrong charge, the gap is open, right? We don't have this problem. So, which means again, another alternative would be to rerun everything with HSE or PB1 functional to open the gap and then again eliminate, get rid of this problem.
Yeah, and so when this is done, when the HSE is done for the no charge, I'll compare it to the charge one that's running, and just we'll look.
I hope you're not waiting. You also run this job right away. Right?
Yeah. So, so that's what this is about. So I was going to compare that with. Oh, I don't have it on the next slide. I have it in a few slides later. So we've looked at the molecular dynamics portion of it and how it's kind of affecting the energies and the distribution of the charge. And now we're going to look at just a few of the results that come from the electron dynamics. So I'll take some of the surface hopping data from Peng that he had, and I'll show some examples of the red field data that I produced, do a comparison of some of the time scales, but even looking at how these rapid fluctuations are occurring from quantum dot to die may help me make some sense of some questions that I had. With our red field tensor, and looking at the relative transition probabilities, we've seen these over the last couple of weeks. This is looking at the entirety of the system. This is just the nicer image localized around the homolumo portion of it. So you can see here, this is kind of the homolumo, and we're just looking at a small portion of that in different coloring. One thing that I noticed, and that I was thinking about on the way here, so if we look at the amplitude of this red field tensor, we'll see it goes from 0 to 6, and normally we have it from 0 to 6, but a 10 to the negative 3, and so
so it's much
when I was thinking about it, we take
larger, right?
Right, so it's much larger, but then part of me was wondering about when you generate, if there's any type of scaling when you calculate the real files versus our coupling files, if there's any time scale difference, because we take our couplings in our R matrix and then multiply it to get it into the right units. And so that's something I just need to go back and look at, because it should be that they should be the same.
So what again you convert to the right units? Couplings?
So to get it in our MATLAB code so that it has the right units of time, it's just taking times a factor of 3.
But you're converting to time. What is converting to time?
What is the POTIM step?
Time step, right? This was my question. I think we typically have a port, if POTIM equals to 1, right? So then the time is just femtosecond, so it's a real time, right?
Yeah.
You don't need to convert it to anything.
Right.
If it is with a larger step, which is typically for inorganic materials, I don't know, for silicon you also were doing this or not?
Seems like
One? Oh, but for titanium dioxide, you were taking larger?
no.
Taking 1.
Oh, okay. But yeah, so for cat selenite, lead selenite, we make in POTIM 5 means you kind of have a larger step
You don't have
in
any
a time.
vibrational frequency slower than that, or faster than that.
Yeah, but I think in this system, I hope he didn't do it. I hope he was really doing with every femtosecond.
Right.
Then there should not be any units conversion or anything, multiplication or division.
Right. No. But anyways, so these very large, tensor elements or transition probabilities leads to very, very fast relaxation times, which is ideally what we're looking for. So what we want to have happen is
But this probably again based on the very high couplings.
Mm-hmm.
Like I think if we compare just the average, like if we calculate the average couplings, and I have the scripts, Jabet can help you with it. How you can calculate.
This is basically an average over all your couplings.
Okay, yeah.
So
I think it also would be much larger values comparing to, let's say, just bare quantum dot or like other systems you were working on. And again, this might be really due to this artifact of the degenerate state. Because in a couplings, you also have energy difference is also contributing kind of, in your, I think it's in a numerator or denominator, don't remember where it is, but it definitely contributes to have you write, like again, you have you have this energy splitting right in between the states is already kind of inserted to the couplings.
Right.
So if you have degenerate states, of course your couplings is growing just due to this fact. Plus, it's also kind of artificial delocalization, or how say, hybridization of orbitals. If the states are degenerate, then any quantum software will just decide, if the state is degenerate, then where it should be localized, on the quantum dot or on the die. Or maybe it's a superposition, right? And then if it's a superposition, then this is our hybridized states. And of course, then your couplings not coupled between localized orbital quantum dot versus localized orbital of the die, and then just switching between them during the time. It's really just hybridized state. And then of course the couplings will be huge. So there are two artificial things. There are two artificial kind of effects which both just originated through these problems that our homoluma is too close to each other.
And so these are two examples of the timescales for the electron hole relaxation using Redfield theory. So I'll start here. So this table up top is just a list of the highest oscillator string transitions. So these are the most probable optical transitions from the system that I calculated.
But can you say where you excite? Like if you go to your absorption spectra, can you just kind of at least roughly say where you excited?
Yep, so I'll highlight this first before I go back there. So this D is just the excitation energy. So we're looking at energy differences between I and J of, close to 2.2, 2.7, 3,
so but
2.8.
which peak it is? Like
So,
it's your second peak or?
Yep, so it'd be
peak?
close to the secondary peaks. So because we're looking at, this 2.5 region, and then close to, again, 3. So then we're looking up here. So these.
Oh wow! So it's really excited very high.
Yep. So there are some here, and then at these major peak points is kind of the distribution of where those absorptions are coming from. And so, so when you get to the 2.0, 1.9, those are that first front end peak. 2.4, 2.2, those are kind of the secondary, and then we get to some of the higher ones. And so in the majority of these types of transitions, you're looking at quantum dot to quantum dot transitions lining up with what the absorption spectra said. And if we're looking at these dynamic plots, we're looking at this red is where the electron has been populated, blue is where a hole's been generated. And so you can see that, even on a log scale, I only have it plotted from -3 to -1. So we're looking at a femtosecond to 100 femtoseconds. And the relaxation times are happening here, just past 10 femtoseconds. So we're on a scale of, tens of femtoseconds. So it being an ultra fast relaxation process for both the electrons and the holes in almost all of these.
Well, for electrons, you're already there, right? It's nothing to relax, actually.
Right.
You're already at the age of the... But for holes, you are having a super quick...
Right. And I mean, it's... So part of that is, these tensor elements are going to be really large, and so the transitions are going to be calculated fast.
But can you really... I guess you didn't check, but where you really excite, you think you're exciting the quantum dot to quantum dot transition at this kind of brighter state?
So I'll put the same PDOS data that I had earlier, and I have it for these states. I just didn't print it out here, and so then you can see where it's kind of localized to where it's going. And so, the good thing is they're both on the same magnitude of the time scale. Because it's important to have both of the charge carriers be at about the same rate. That way you don't have a buildup of one and have recombination occur. So
again, 100 or 10? 10 femtoseconds.
It drags out a little bit. So you're looking at 20 to 50 kind of femtoseconds in this range here. And so
it's less than 100 femtoseconds.
Less than 100 femtoseconds. Wow. And so when I was looking at some of the data from Peng, looking at his type of exponential fitting to the electron and hole relaxation, well, here's his 100 femtosecond mark, and you're seeing the bulk of the relaxation occur inside 50, 60 femtoseconds. So you know, both methods are giving very similar results, even for both the holes and the electrons. And so I'll have to go back and talk to you guys a little bit about where you decide that relaxation occurs. But I mean, just fitting those rates to the exponential fit, they're going to be very, very similar. So when we were talking earlier about those sharp edges in that PDOS at the HOMO edges, so one of his calculations, or he had plotted out here, was the population on the die, which is on top, and the population on the quantum dot, which is on the bottom, as a function of the first 100 femtoseconds. So you can see on the die, it starts at 0, and the quantum dot starts at 1. So we photoexcite the quantum dot, and as we go through time, you're looking at, you know, the electronic population, and then you get to this area here where you have these huge switches of the charge hopping from one to another. And so I don't know if that's, I'm trying to think if that's the same artifact coming into play, or if you really would have that drastic of a jump, or just because your gap is so close that it's jumping from one to another, because I don't.
But this jump happens at which scale? I can
so it's about 15 femtoseconds, kind of
even quicker than your final. Okay. Yeah, probably by that again. Somehow the relaxation, like even if you excite at kind of a deep hole, right? So really deep to the valence band, it looks like somehow the relaxation to these edges of this unclear HOMO-LUMA ranges, right? Of these kind of sparse states which we don't know where to address, is happening extremely fast.
Right. Well, and I mean the density of those states in the valence band is very, very dense. You know, versus the
we
valence
see the same
band.
thing with a quantum dot, with a bare quantum dot, right?
Yeah.
Oh, and the relaxation is not as quick. It's picoseconds, not less than 100 seconds. So it's really kind of some interesting behavior of this system, and it's really it looks like it's probably not really so much related with the problem of the HOMO-LUMA question, right? Because for electrons for sure it does, but because you excite it very close to the edge of close to the band, what we call band gap. But for holes, it looks like you're exciting it at almost 2 electron volts below this strange area, right? So means that you should be there kind of in a regular quantum dot states, and it's reaching this age of states very, very quickly, which is really strange. I don't know what exactly is the origin of this behavior.
I'm going to ask you a question, which Daniel may answer on Friday. So, do you see any connection between this feature and the approach practiced by Oleg Prezhdo in his papers, by splitting electron transfer, charge transfer onto non-adiabatic component and adiabatic component? Would it be possible to call this adiabatic charge transfer? I'm not telling that it is. I'm wondering myself.
If you return back to your figure for the density of for the
fluctuations.
Yeah. So this is your adiabatic charge transfer, right?
But it looks very similar, but I'm not 100% sure if it would qualify.
Okay, right? Because if you would have crossing without actually allowing it to cross, and just so it's fluctuating between indices, switching.
Mm-hmm.
Well, yeah. Yeah, I mean.
Daniel, you will tell what is adiabatic charge transfer.
Yes.
On Friday. Thank you.
Yeah. So we'll have to sort some of this out, but we're getting there. So that's kind of the story on this set of systems, and I'm sure, well maybe not sure, but in a couple weeks go through our other set of organic systems for photocharge transfer. But you know, an important part we talked about in the beginning is looking at the charge of the quantum dots based on the deprotonation, how the ligand is binding to the surface of the quantum dot, and how important that charge is to the energy spacings and the opening of our gaps so that we can go through and get our relaxation rates. And so when we're talking just briefly now about some of these, you know, really closed band gap issues with index swapping or adiabatic relaxations, and so just basically riding that potential. We need to get that ironed out so we're not having these artificial switchings happen. And then, you know, the relaxation rates, the timescales are just really fast, faster than they probably should be. So we'll have to look at either qualitatively looking at relative timescales and trying to extrapolate out to other systems, or
Can
looking
you return
at.
back to your figure with your charge, no charge, ground state, density of state? Yeah, this is where I'm comparing. I'm kind of thinking like, again, can it be such a fast relaxation against some kind of effect of this not properly charged system? And yeah, of course they are shifted, but I don't know, the density of states looks not very different between.
No, I mean.
So the blue one, no charge.
Right.
So like all features are the same, or
right. They're very, very similar in terms of, you know, what the peaks are. You have a little bit of difference.
But I would not go so far away, like kind of thinking about the area where you excite.
Yeah.
It kind of 2 electron volts below this coma range, right?
Yeah. Yep. So kind of
and
first,
then
this
it's
first making peak.
like on this figure, it's probably hard to see. Like it's.
Yeah. So this is the no charge right here, and this is the charge. So I mean, the main difference is you have just this little bit of a, you know, protrusion on the valence band edge where it looks like there's one more peak, so you have that extra shoulder. Whereas in the no charge, you know, it sits all the way up here, and here this kind of pulls away, versus, you know, these just kind of almost twin peaks. So it just shifts it just
But
enough.
overall, at this range, 2 electron volts from the edge of the valence band, of the edge of the valence band, right?
Yeah.
So if you compare, like you have this 3 sharp peaks. There it's like 1 sharp and then kind of more smooth, almost featureless peak. And this might also, which means in this case you have some kind of sub bands, sub gaps in the valence band. Here you probably have really very smooth states. So, and this also might be affecting the quick relaxation of the whole.
Yeah.
Maybe, I don't know. Well, at least because the density of states are not exactly identical. I mean, I agree. The far away you go from the valence band, from the band gap, they look more and more alike. But in this area, you see some significant features, which are really make these guys very different. So overall, I mean, it's mainly really the effect of the charge, not only because of this closing the gap, but because of these changes in the electronic levels.
Right. Yeah. Because I mean, if it is, you know, the other thing when we were talking about where is that extra charge localized, should it be on the carboxylic group? Well, if you have it where, I mean, that's where your main feature changes are. You know, those states are localized on the die, so you know it's somewhere on the die because that's where the states are shifting a little bit.
If you're adding or removing 1 electron, should it be spin polarized?
It depends on the initial system.
But either one of those needs spin polarized.
Right. So
which one has unpaired?
So in this one is unpaired. In some of our other systems that we're looking at, adding the additional electron puts it back to an even electron count. It just depended on the chemical makeup.
And in your electron added, it looks like there is still. Can you slowly move your higher up, higher, backwards to the negative, to the stop here. There is a white spot.
Yep.
So it means it's still missing.
Occupation.
Yeah, because we lose electron. It has to be there.
But there is a missed electron in both configurations.
No. In one configuration, you have all electrons.
So there's a no charge system and then an additional electron. But yes, in both density of states, there's a partial occupation missing. So if I go to this one, so you can see it right here. There's a small space where it's not completely occupied, and then here in the no charge, there's a small space.
Would it be crazy to add 2 electrons?
No, I've also tried that, but that pushes everything above the band gap, and so then there's the conduction bands populated, and so then you get something similar to what I had in here, where you have almost no gap because it's just a continuation into
Well,
the states.
I think the easiest way to really get rid of this, put a proton on a carboxylic group, right?
And just take one of them.
And then it's neutral, and
remove,
then
remove one of the bonds and just remove a bond and just protonate the
Yeah.
oxygen.
well, kind of, you don't need to remove. You just put the proton, and then
And
it
then
will be
share it.
optimized. Or
Yeah.
when you run the dynamics, it
Right.
will
It,
kind of
it
put
should-
itself in the right way.
Yeah.
It will probably kind of losing this strong coordination with the cadmium, right? Because proton is there. Or maybe it's actually deprotonated naturally. It might also prefer to lose the proton,
Right.
and proton
And
will
just
go
see that
somewhere
just
to the
kinda
surface.
somewhere.
Yeah.
Yeah.
So actually, I don't think you need to optimize the structure. You can just put a proton, kind of run the dynamics for first how many femtoseconds or how many picos, how long are you need to do the non-abatic dynamics to apply your Redfield theory?
10.
10?
I mean, I would.
10 picosecond?
I mean, femtosecond.
Oh, 10 femtosecond.
I
Wow.
mean, we normally we run for a picosecond, but since you're averaging over couplings, you can run as few or as many as you
It just
want.
increases error bar in the
Yeah.
reported
Yeah.
rates.
Yeah. So I mean,
Well,
I could run
as
you
I
know,
like-
3 to 5.
Then it looks like you can like looks like to get up to 100 femtosecond, like really rerun all this dynamics, probably not a problem at all, right?
Yeah.
And you already start with HSE, kind of exactly same settings as kind of not real, not accurate, how to say, neutral, but in the wrong way,
Yeah.
right? So with a lost electron, then you will add the charge, and also probably do HSE calculations, because they definitely will open the gap, and we will get rid of this problem. And then protonate, put a proton. So like, don't optimize, just put a well, of course, figure out what would be
close.
reasonable distance,
Yeah.
oxygen, OH bond from carboxylic group, and think about angles are pretty flexible for hydrogen in this case. So put a proton, put a neutral, and then of course it's a neutral charge, right? And also run at least 400 femtosecond.
Yeah, and just see what
Also with HSE,
Okay.
right? Because
Okay.
even with protonated system, we might still have might have a very small band gap. In this case, the gap is reduced not really because of the charge, but it's also reduced because we have states from the quantum dot, or let's say states from the ligand, or from the dye, right, localized on the dye. They're kind of getting inside the band gap of the quantum dot, and that's why they can really come very close to the edge of the conduction band and kind of close the gap. And if your gap is already too small, for about 1 electron volt difference with this functional, right? Instead of 2 electron volts, we have only 1 electron volt band gap for the PBE functional, for the pure GJ functional, and then kind of adding these states coming from the ligand, of course, will be closing the gap whether you have a charge or not have a charge.
Right.
So that's why I think if you already start running HSE and you can do it, right? It looks like you don't have any technical issues with that, at least for how many femtoseconds have you done already with HSE?
Well, I
At
mean,
least
I set it to run 100 steps, and it was up to about 60, and then the power went out,
Okay.
and so it's
Okay.
back to like
Yeah.
a little over 20. So I mean, I could stop it.
I
'cause
imagine-
the energy change in between steps really isn't that large. It's getting close to my convergence limit. So I mean, I could just kill it and look at what it is, or just pull the
Or
information.
just continue, you don't need to
into
kill, like,
Right. Just put it in a new directory and look at what it is.
Yeah.
Yeah.
So, but I would suggest like 3 calculations, but with a different functional, and then we can use this preliminary data just like more technical issues for really showing that GJ function is definitely not a choice in this case, right? And then effect of the charge and so on.
Yep. Okay.
Yeah, and we probably will not have, again, if we don't need to really run up, if HSE is opening the gap, and then we don't have the switching between different types of orbitals, right? If we see Luma will be always on a quantum dot or whatever, on a die, HOMA always on a quantum dot or backward, right? So then, kind of, we don't need really to run for so long time, and yeah, you just take, I would say 10 maybe too small, but at least 100 femtoseconds.
100 would be sufficient.
Hopefully,
for
hopefully this
first
would be
look.
enough with the Redfield theory.
Yeah. Yeah, I mean, other than that, that's basically
Yeah,
it.
so you just restart 3 jobs, right?
Yep.
One is really putting the extra atom, right? And it's probably the most significant change in your overall files. The other ones is really just playing with the charge and the functional.
Yep. That's it. Unless you got questions.
Questions 1,
No,
Questions
we
three?
go everyone.
question 3, and now we start the circle.
Introduction. So you have two systems. One is no charge and another is one electronegative, right? So for the rate field tensor in the dynamics calculation, you calculated for one electronegative.
So for the red field, so it had been done, someone else had done the coupling calculations before me, and I don't believe they used an extra electron in those calculations, and so I just have those coupling files. So what I have for the red field is without the charge, and so, yeah, I mean, I guess it wouldn't be hard to go back, just take 100, well, I could just take 100 of his files, add a new in-carge, run the couplings, and then we can compare that way. That would be simple enough too.
So you actually don't know.
Not yet. No. I mean, with the way it looks, it doesn't look like he put an extra charge in there, but
No, for sure it was neutral.
yeah.
For sure.
So,
He just didn't know how to do it.
oh, okay.
Because we discussed it.
Oh, okay. So yeah, so that'll be something.
I just was hoped that, like, my suggestion was to put a proton, but I think he didn't put a proton, he said, oh, put a proton and then don't worry about the charge. He have heard the last part of my sentences. Don't worry about the charge. So he didn't. We go this way then. It's your turn.
I didn't have any specific questions today. And you can go away again.
Okay, we return to
Chapter.
chapter.
And where's the extra charge? Like when you put it in, like where is it located in the model?
So that was when we were looking at, this change in the PDOS portion of it, and looking at, so this extra shape here on the edge of the density of states, kind of what we were talking about earlier, is the main change in the electronic structure. And so these states are all localized on the die itself. And so not only is it flipping where the HOMO level is, it's adding that charge onto the die portion of the molecule.
But can you say exactly on which portion of the die?
On which portion?
Because you
Not-
expect
not-
that
not from
this charge should be on the oxygen probably.
So you haven't looked at the power charges yet?
Yeah, so not from this. I would have to go back and count which exact.
But this is a
oxygens
portion
it
of your
is.
projected dose, why not?
Well, so this is just.
Oh, because
the
it's
HOMO
projected
level.
dose, it's not really for the entire system, it's not
Right.
total charge, because of course you
Yeah.
expect the total charge should be coming from the carboxylic group.
Yeah. Yeah.
It should be localized on the carboxylic group, but
Yeah.
but not necessarily that your HOMA will be really associated with the
Right.
carboxylic group.
Right. So this is solely for the HOMO level, and the charge is off of the HOMO. It's nearby, but it's not localized there.
Mm-hmm.
But it's a
we
good
have an
question, we need
yeah.
total distribution of the total charge
Yeah.
to answer this question. Because then we clearly see how the
Yeah.
charge is distributed, neutral versus not. I think we will immediately see the difference.
Yeah.
Yeah, because if you knew where the charge was located too, that would give you an idea of how it would impact the rates during the dynamics.
Yeah.
But again, intuitively you expect that this should come from the carboxylic group, right? Because this is the source of your charge. Either protonating or deprotonating, you really have in this electron in the carboxylic. And then wherever the carboxylic group is mainly contributing, this is where we have the most impact.
Yep.
Good question. So should we go, Ben?
I don't have any questions.
No, you have to. You can just wait for a while to
I don't think so.
Okay,
Yes,
but
no,
we return
sure.
back to you. So you have to have a question.
I have two very generic questions.
Do you want to
Share one question.
Yeah, yeah.
maybe this jab it?
So, for my first question, I know you talked about it, but I must have just zoned out when you said it. Why are you redoing the calculations?
So when we're looking at where the charge is localized on the system and where we
Return
can
back to your structure. Or to this one.
Yeah. So we're looking at it because, so the HOMO level right now, you can see is localized on the die. And the LUMO is localized on the quantum dot, as it should be. In the calculations, without specifying this extra electron, you get some mixing, and so these states will swap with each other.
So did he, was his data published or not?
No.
No, okay. Alright, so
We
you're just
want,
going
we
back.
want to make them publish, that's why we're trying to figure out what's going on there.
Okay, that makes a lot more sense.
Yep.
'Cause I understand. So, wait. Okay, so my second question is, what would this be used for?
Of the system.
Yeah, I'm not familiar with it at all.
Yep. So in this type of metal organic Ligand quantum dot, so we want to absorb light on the quantum dot itself, have the hole relax to the die, and once we have the charge outside on this ligand, we can have some type of chemistry happen with this extra charge localized on the die. So you can have redox chemistry, you could do oxygen generation, that type of photocatalytic reactions.
So there are two applications. One is use this system for the photovoltaic, and the second one for the photocatalysis.
Okay.
So for photocatalysis, the idea is that you need the ruthenium 2 plus has to be switched on to ruthenium 3 plus. And it's known that this complex is, you can modify ligands, but mainly it's ruthenium property. It really works as a good oxidizer. So
Okay.
you need to really switch your ruthenium 2 plus to ruthenium 3 plus. And that's why we need this charge transfer, whole transfer from the quantum dot, right? You photexcite quantum dot, and then whole transfer. You also can think that you can get 3 plus if you photexcite the die, and then you will have electron transfer, excited electron going from the die to the quantum dot. Then you also will get 3 plus. Why we don't go this way, you probably can answer.
Well, so
Why we really want to excite the quantum dot?
the quantum dots are going to be more stable and they're also more tunable, so we can range the exact, depending on the size of the quantum dot, range the exact absorption energy that we're interested in.
I would say the main reason is it's more photostable comparing to the dot. So it's can be like you can really shine light many, many times and quantum dot. And the second reason, it's a carrier multiplication processes, which can be utilized here, right? If we photexcite the quantum dot at a high energy levels, then like in a femtosecond range, the carrier multiplication takes place. So it means now we have pair, from one pair, right, excited pair with high energy, we're now having 2 pairs of electron hole pairs, right? So which means now you can transfer 2 electrons almost simultaneously. Oh, not electrons, holes if you want to transfer holes. 2 holes can be transferred simultaneously to ruthenium die. And why we need two? Why we need more carriers? How many electrons are needed to oxidize the water for the oxidation, half oxidation reaction for water? Well, you need to write the equation and balance it. Anyone remembers? Or anyone can do it on a blackboard and show how to balance the water oxidation reaction? Well, technically you were talking about it in a general chemistry, I think, where you were talking about the redox reactions, right?
Okay.
No?
I mean, I remember, but it would take me a minute.
2 electron, right?
Anyone can balance or write the equation
For
water oxidation? Well, water oxidation reaction, what's the problem?
Why the 2
you're going,
electron?
H2O, so 2 H2O to H2 and, 2 H2 and O2.
Then you have to balance it, so you end up with 4 electrons. So to have this reaction, you need 4 electrons. And again, this 4 electrons comes due to the balancing the equation of water. Water H2O going to H2 and O2. So you should lose 4 actually it's not adding, it's losing 4 electrons for the oxidation, right? And adding electrons for the reduction, yes. And these 4 electrons have to be done, actually why for the oxidation of water is still kind of a challenge. There's many oxidizers are known, which can oxidize and transfer 1 electron, but you need 4 electrons to make it efficient, and you have to have 4 electrons simultaneously. Not like in a step reaction, right? One and then another one and then another one. You really need to have them all together. Then it would be very efficient processes. Then you can oxidize water right away, and then we can use hydrogen and oxygen as just compounds and really use it for the how's it called, electric power plants or something like this. So if we have carrier multiplication, it already provides you more carriers simultaneously. Well, we still don't have 4, but at least 2. 2 is better than 1. So you probably also expect that if carrier multiplication really can take place in the system, then your oxidation processes will be efficient. More efficient rather than through the single electron photoexcitation processes. So two reasons why. One is for the stability of the quantum dot, and second is the carrier multiplication, which is known for these systems, for the quantum dots. Good question. Done? Or you have a third one?
Oh, no.
So, I had a question when it comes to the BDOS screen. You said something. I'm not too familiar with the term. What does it mean when you take a single point of something?
Sure. So when I show you this, so this is the entire multi-molecular dynamic trajectory. So if I'm taking a single point, I'm chopping just one. So time 500. This vertical slice of all of these is one single point along the 4,000 femtosecond trajectory. So all I'm doing is I'm looking at one small piece of it and just looking specifically what's happening right there. So yeah, so when I was doing this, I was looking at 0, I was looking at 100, 200, 300, and so just yep. So instead of looking at everything in between, just solely picking, I'm just going to take a few small ones, take a look at what's happening, see what's interesting, and then go back in more detail.
Okay.
Yeah. So so that way, at each single point, you know, the atoms are oriented just a little bit different to one another because of the dynamics. And so, how are those specific adjustments changing what we're seeing?
Okay. Thank you.
Yep.
On your plot with like all the different orbital energies like plotted out through time, you have like 2 energy gaps there kind of between your bands.
He has 3 energy gaps, I would call them.
Well, yeah, I don't know. But like, why are there multiple gaps there? I guess that doesn't really make a lot of sense to me.
Sure. Well, so two main parts, I guess. So earlier we were talking about, so we have our dye and we have the energy levels contributed by the dye.
Mm-hmm.
And we have our quantum dot and we've got energy levels contributed. So depending on a specific dye and quantum dot system, how they overlap or intertwine is going to vary. And so when you start having energy states from one portion, you know, being inside a band gap of another, like a quantum dot, you're going to start having, you know, a distribution with some of these spatially separated energies. Another portion of it is once you start adding other pieces together, like a dye and a quantum dot, then you start to have a shift in total energy because now you have a little bit of a increase in Coulombic interaction between electrons on the dye and electrons on the quantum dot, and so it shifts it just ever so slightly. And so that's why you start to see just slight variations and states being intertwined.
Okay.
And can you return back to your DOS, like, you know, single point DOS? Yeah, if you look, like, doesn't matter right or left, look on the unoccupied states, right? So you can see like these sharp peaks also.
Yeah.
So actually, this is your 3 bands.
So,
right? And again, it's might be also technically in quantum dots due to the confinement, right? You expect the discrete levels, right? And in Illum, it's a most pronounced comparing to HOMA, and usually we have like a few low state creating really kind of a gap, or how to say a band, which is, or sub-band, which is pretty much separated from the rest of unoccupied states, and having kind of this sub-gap very close to real gap. But plus contribution of dye molecules, which also have to be more discrete. So confinement effect.
Okay.
Yeah, and if I went to broaden these and just, you know, had vertical lines where the energy levels was, you know, I'd just be here, here, and here.
Mm-hmm.
It's just that the broaden just so it looks nicer.
Okay.
So I have a stupid question.
Ooh.
So you have drastic changes in populations with what seems to be almost like adjacent time steps. In other words, it doesn't take many, many time steps for a significant change in population to be observed. Just a small change in time sees a drastic change in the population for your HOMO. So I assume that this is correlated to some geometrical degree of freedom in the dynamics. Do you know which portion of the geometry changes in order to make that influx in, or to make that a drastic change in population? And if so, which degree of freedom is it?
So if we're looking at that PDOS plot, now I'm assuming this is kind of what you're referring to, just how drastic of a change there is. So in this, it's not so much that there's a dynamic driving force, but it's more the way that
Degeneracy of the HOMO and
yeah. So the HOMO value that's calculated to be HOMO, where the Fermi energy is at, and then where the next state above it is, are so close together that along the trajectory, the populations fluctuate just a little bit, and so then the HOMO shifts from one to another. So the Fermi energy kind of jumps back and forth over top of one of the energy states. And so that's why all these states, these super high population states, shouldn't actually be there. They should be where they're at when it's at a low population. It's more an artifact of the way the population is assigned in the calculation than it is in any type of molecular fluctuation or geometric change.
So can you correlate that drastic, or well, I guess it's not such a drastic change in the electronic structure. It's just a subtle change in electronic structure leads to the drastic population change.
Right.
But so
because it's assigning the population to a different state, whereas it should be to another one.
But,
right. Yeah.
But this is very important point.
Yeah.
Like, again, as soon as we believe that what we're getting at really physically reasonable data, right? So to check how this electronic change in the trajectory, or how these fluctuations in the electronic trajectory related to which type of changes in geometry, in other words,
right.
kind of normal
Yep.
modes, right?
Yep.
Is of course possible, and of course it's a very important question to address.
Yeah, and
Okay.
so Peng did have a couple plots with frequency values plotted for the system, and so once I can isolate, what the frequency of these fluctuations is, I can go back and see if he had it assigned to a specific motion, and if not, then yeah, I can definitely go back and look at that and try to assign it.
Perfect. I'll ask the same question next July.
So I have a question off of Brendan's. So how will the non-adiabatic dynamics be affected if you have your adiabatic states change from a ligand-based state to a quantum dot-based state during your dynamics?
But this is exactly what happens.
Yeah.
Yes, but how will this affect the relaxation and all of the properties that we're interested in? Because it would change the nature of the state. Therefore, the non-adiabatic couplings would drastically change as well because of the overlap being a different place in the system.
So
yes?
Yes. So with our Redfield method, so we look at a ground state configuration of the electronic structure, and we base, so the coupling values are assuming that the charge is localized on that state. As we go from one time step to another, it's going to take the coupling between those states. So you're going to have a reduction in population or an increase, just depending on where they're spatially localized. But it would be something that would be, I wouldn't say, unbeknownst to us unless we went back and did like these partial density of states. So I would have to look at specific coupling values between the two different sets and then do a comparison to actually know if it's helping or hurting the overlap, and then that would, affect the rates from there.
So on your time-dependent Consham plots where you just plot the energy versus time for each, this one, do you see much avoided crossings, or are they kind of well-defined?
Well, it's hard to see because they're plotted as adiabatic states. With different systems, it's been easier to see if there would be some type of crossing happening, because it's more of a slow, pronounced type of wave almost in the fluctuation instead of being very quick. So like when you're looking at, say, this red line and all of a sudden it gets very close. So we would assume that these states are interacting and a transition could occur. Or it could be something that, you know, a blue state is actually this red one, and this red one is actually the blue one. So I mean, it's hard to know specifically without going back and imaging the electronic structure at those instances where we think there might be something happening.
So do you think it would speed up the relaxation, like artificially speed it up? Or do you think it would not have any dramatic influence on the relaxation?
Part of it
because you're saying that your time is like femtosecond relaxation. So could your relaxation be due to the fact that you're changing the types of states, which then force it downwards, where it would take longer to do adiabatic, like the coupling between the states? Does that make sense?
Yeah, I mean,
I think it's not. Again, if you look on this projected kind of information on the contribution of orbitals, right? You can notice probably again that the state is not just localized on a die or localized on the quantum dot. This is what we see in the ground state. For the ground state, our HOMO is completely on a quantum dot, HOMO on a die, LUMO on a quantum dot, 100%. Like it's 100% localized state. Donor, acceptor, kind of, you know, very clear picture. However, here, if we look on a percentage, it's really very much hybridized. And you really have, even in a case when we have dominating nature of quantum dot, right, you still have significant contribution of the die. And again, this is probably artifact, this hybridization of the state is probably kind of artifact of this too close, like you have really two states of the quantum dot and the die to be degenerate, which again, the way how the program is doing it, because the degenerate state, then it's just a superposition, right? And kind of and superposition means hybridized state, which maybe not really corresponds to the nature. Moreover, if you use a different functional, your splitting between levels will be increasing. You really kind of killing down this degeneracy, and you will have really 10 times difference in your dynamics, because then you really will have states localized on the quantum dot, states localized on the die. And then they are overlap, even if they switch, especially if they switch, and if at some moment it's in a quantum dot, at the other moment it's in a die, then their couplings would be really very small, non-batic couplings, because they have different localization, different property. But if they hybridize, then you increase their couplings, and then they become really very quick. So it's, I would say, your question really have to be split into two questions. One is not just switching between die versus quantum dot orbitals,
because that could go either
but
way.
also whether you really see this mixing of the hybridization between orbitals, and how really trustable this mix. Like, are we really suppose it has to be hybridized, or it's really artifact of the degeneracy? Right. And if you increase the splitting, you have completely localized there or localized there. Yeah, so very interesting question, but this is exactly why we need to do more, more precise, maybe recalculation of the things to answer these questions. Who was missing? And Javed has a question now.
I have a kind of conceptual questions about, you already saying that if you add a charge, they have a significant changing and everything, like electronic structure to NTOs and everything. So if you apply this system for photovoltaic application, and if you see the charge transfer from the quantum dots to the die, so with the time you will get some charge accumulate in quantum dots or in dies. So in that case, your whole properties should be changed, everything. It could be changed, right?
No, you're talking about different things.
I
The
mean,
charge here, the difference in the charge which he's seeing, it's a total charge in the system. What you are saying, your system is still neutral. When you transfer your charge from quantum dot to the die, or from the die to the quantum dot, you're not changing the charge on the overall system.
so
You
we are
change the
separating
localization of the
hole
charge.
and electron. So if both biases can be different, then if electron is transferred to in other end, so you will get a whole, overall total positive charge in the system. Maybe it's not that big.
No, you don't want to charge your system.
Now, if we transfer the electrons from the one cell to electrode, I mean, well, I don't know.
Okay.
I don't know the term. What's the other side?
So now you're starting like it's nonlinear.
It may be
absorptions.
non-linear, yeah.
Right. And so then you're going to have a whole range of different properties. I mean, then you got to talk to Sergey.
Suppose like if you set a very big difference by adding only one electrons, so it's very usual to get this kind of difference in the real application, right?
So once you transport a charge out, then you're left with another system that has a new charge.
But doesn't
that's
matter.
drastic from the-
Doesn't matter because we need to return it back to the ground state, right? So to get like, let's say you have one cycle, you excite, then there is a charge transfer. After the charge transfer, whatever happens, let's say your electron transfer faster than hole, you still have to wait until hole is transferred, right? Because you cannot excite when the system is already charged. So it really has to go back to the ground state, and then you kind of photo-excite it once again, and then the cycle is repeating and repeating. So you really have to get rid of all charges and get your system to be relaxed back to the ground state when your second cycle is going. And the question is how quickly it's happening, right? So yeah, it involves, you're right. So electronic structure might be affected if your electron is moved already and hole stays there, or backward. Electron is leaving longer.
Your call will be disconnected.
Oh, Braden didn't have a chance to ask questions.
Oh.
Unfortunately. Okay, but I don't know.
Yeah, that might decrease the efficiency of the cell kind of video.
Now this is next kind of step, right? First step is just to see that you really have this charge separation and charge transfer.
No,
Because if your charge transfer not happening efficiently, then next step of where this charge is really going after to be used is kind of the next question. What? Oh.
Oh.
Any other questions? I don't know. Yvonne, do you have a question?
Yeah, I guess I can ask one. So I guess to my understanding, there are two problems. The first one is partial occupation. Second one is index swapping. So I was wondering for the partial occupation, if you include spin or spin, non-collinear spin, does it help?
Well, I haven't tried that yet, so I don't know if you want to go there, we can, but that's no.
Not like again, you not associate the spin with the ruthenium, right? Like this charge, not really. Actually, whatever the number of electrons we will have, I probably still have the even number of electrons.
It might be odd.
Well, because if it's negatively charged, it's even number of electrons. Because you're losing proton, you're not changing the number of electrons. Again, if it would be right charge, which means negative charge when you deprotonate the carboxylic group, so you charge it due to the proton, not due to the change of number of electrons. Number of electrons stays exactly the same in the system if you have a protonated case, right? So that's why if it's correctly charged, then spin should not really have. It's in an even configuration of the spin, and ruthenium was also with paired spin, like in a low spin state. So that's why spin is not really a problem here. If you now, if we have 0 charge instead of -1, means we lost 1 electron. Yeah, then we have non-even electrons. But again, this is probably S electron from 2s state on the oxygen, probably OP electrons from the SOP electrons, probably S electrons. I don't know what is lost first. Probably S electrons. Which again, it's not really as kind of say not really spin in a way how you talk about transition metals, right?
Okay. So another question is for the index swapping. So you are going to try different functionals or different methods. I was wondering if you can just try DFT plus U to open up the gap.
I mean, we could do that because that's, I know Hung applied a scissor operator in some of his plots that he had, and so just artificially opening the gap. Would be an option. It's just.
Well, but again, what's the benefits if we can work with HSE, which is proving to be really much better functional?
Yeah, so
where
it's
just a
more
pure GGA.
expensive, right?
Well, it's more expensive, but again, if it's doable, it's more reasonable probably to go to more accurate methodology rather than. I mean, I just doubt that. Have you ever tried dynamics with HSU with a plus U term?
Yes.
Oh, you did, right? So technically, it's not an issue. But there are a lot of issues again for the complexes. If it would be organic molecule, it's one thing. But because we have this metal organic complex, there is several papers where people talking that your plus U will not give you the right electronic structure for metal organic complexes. We're not even talking about quantum dot or interaction between them, which might change the electronic structure. Mainly because you need to have a different U portion. Usually you put U portion only on the metals, right? But it was kind of proving that you also need to put a U portion on the P and D electrons of organic part, right? So, and it's actually different portions, so it's really kind of more complicated way how you have to define your U. You have to justify, probably again use a absorption spectra to justify that your electronic levels are right for this molecule, right? So it looks like technically it's not so easy to assign it correct.
Unless you're going to run for a very long time, then it.
There was also an issue with HSE. It requires also much more memory. And then with old machines, like now on the CCAS, we don't have this problem at all because we have really increased memory pieces. Before, with the very old clusters, we were restricted with 2 or 40 gigabytes, like cluster 1, cluster 2, whatever the old ones. So then, actually, we were not able to run these hybrid functions because we didn't have enough memory in the nodes. And then, then plus U would be the only option in this case. But for our technical issue, for our technical opportunities here with CCAST, looks like it's also not an issue anymore. Good, we done?